Okay, good afternoon, everyone. How are you doing, kids?
Good, how are you?
Doing well? So, plan for today. We are going to discuss one more time a little bit more detail about the PWM. Remember, last week, may I have your attention, please? Last week, we've discussed a little bit about how to design your filter circuit, how to calculate your proper resistance, proper capacitor, or I would say capacitance in order to design your low-pass filter. And then today, I'm going to also add a little bit more detail to the existing information, few more examples to solve for you. And then right after that, in the second half of the class, I'm going to focus on stepper motor. And I'm going to come up with a little bit more detail about the structure of a stepper motor, what's the difference between a stepper motor and DC motor. And then hopefully these are going to be good enough for you to understand PWM, the advantage of the PWM, and of course, how we can use them for embedded system. So stay with me. We are going to have a little bit more discussion today, and we'll go from there. Before that, if anyone has any question for me, feel free to ask. Anything about whatever we've discussed last week? Yeah.
Not about last week, but the lab, is it open?
Yeah, lab is open. I just come from the ETB. Lab is fully functional. We are going to have just a regular lab tomorrow. So I'll meet everybody in there. So let's start with where we have left. Remember last week, I solved one example for you about how to design your filter system. And of course, later I added a little bit more information about how to calculate your highest and lowest frequency. Still they are here, still they are available. Unfortunately, last week while I was teaching you, I forgot to share the screen, although I already posted the recording on YouTube for you, but I forgot to share the screen. But still, since my verbal explanation was in there very clear, I decided to share it in case you want to listen to the, still even behind me, you can see a little bit of the screen in that recording, but quickly right in here. This is what I've solved last week for you, how to calculate your highest frequency, how to calculate your lowest frequency. And the solution is also already posted on Avenue. You're more than welcome to go look at my solution in case you need a little bit of more review about this one. So today I'm going to create more space in here. I'm calculating another similar example, which is going to be the example 4. So I'm going to have, again, XTAL one more time. Everybody knows XTAL. I've already said it, but what is that? XTAL stands for crystal frequency, right? If that stands for your crystal frequency, you can using the same method. Look at here, for example, if your crystal frequency is 4, if you divide it by 2, you can calculate your bus frequency. Therefore, we are going to use the same method again. I'm focusing on example 4. I'm having the same XTAL or crystal frequency to be 4. And then this time, by default, bus frequency is given. But if it is not, I know that everybody knows, just dividing this, you can calculate your bus frequency, which is 2 in this example. And then you are expected to find the value for your PWM clock. And if you want your clock SB to be 2500 Hertz. So how do I do this one? I'm going to use the same pre-scaler and scalar. So I don't draw it once again, but just have it in mind. What I'm using the same PWM clock for the pre-scaler and the clock for the scalar. These are my scalar and pre-scalar from the data sheet one more time. And then I'm going to use those information right in here to calculate the requirement for this question. So I'm going to say clock A clock A is my main bus divided by my prescalar times scalar. My prescalar times scalar, right? I just show you my prescalar and scalar. My main bus or bus frequency, I just have it from here. So I use 2. How about my prescalar? My prescalar, remember, is 2 to the power of 4. And my scalar is 2. And 4 is like the n, right? In here, I'm having n2. Therefore, if you calculate this one, you're going to have 2,500 hertz. Now, I'm going to use those information. I'm going to say 2 to the power of n1 and then n2, scalar and prescalar, okay? n1, n2, scalar, prescalar from here. n1, n2, scalar, prescalar. I get them from there. It becomes 400. So now, if I have any combination of n1 and 2, I'm going to write it, any combination of n1 and n2 that satisfy the 2 to the power of n1 times n2 equal to 400, I'm going to have like the same clock for B. This one's supposed to be, if I have any combination of n1 and n2 to give me that 2n1 and 2 become 400, then I'm going to be okay. Therefore, I'm going to say my n1, if it is 3, if you put 2 to the power of 3, then you have 400, you rearrange it, you can calculate n2. In that case, your n2 could be 50. And next time, if you have n1, 2, then you have to say 2 to the power of 2 times n2 equal to 400. Then you can again calculate n2. In that case, your n2 is going to be 100, right? So this is how you can calculate your clock SA or clock SB. Make sense? Yeah. 400 is coming from like the prescalars and scalars. So if you have any combination of 2 to the power of n1 and to be assigned to 400, then you are gonna have like your prescalar, or you have your clock SP to become equal to this one. That comes from the scalar and prescalar. You don't have to calculate that 400. Yeah. So any combination of n1 and n2 that satisfy this, like 2 to the power of n1 times n2, like equal to 400, can be used, right? Now let's look at another example to make it a little bit more understandable for you. Example 5. I'm going to practice one more example in here. Example 4 is now looking at clock SB, right? It was 2,500 hertz. Now I need to find out the value for PWM, prescalar, and the duty cycle if we want a PWM frequency to be 50 hertz with 60% duty cycle. How do we do that? Let's practice this one. So I'm going to have like PWM ER to be clock frequency over PWM frequency, right? If these two are given, clock frequency is given 2,500, PWM frequency is given, which is 50. It's just given right in here. Look at here, 50 hertz from the question. Then I have to include it in here. Most of them are hertz. I don't need any conversion. Then I'm gonna have my PWM PER to be 50. Now, how about duty cycle? For the duty cycle, I'm gonna say PWM DTY, standing for duty cycle. Question is asking, I want it for 60% duty cycle. Therefore, I'm gonna say 60%. And I already calculated ER to be 50. Then I'm gonna say 30, right? Therefore, I can say the PWM ER must be equal to 50, and then the duty cycle is 60. So my PWM duty cycle is going to either 60% or 0.6 times that 50, which is going to be 30. This is how we can calculate it. Any questions so far? Next, I'm having a piece of code which is going to be really beneficial, especially for your lab tomorrow. In this code, I'm asking you, suppose that your crystal frequency right in here is given to be still 5. And again, bus frequency is half of the crystal frequency. This is the rule always. Bus frequency is half of the crystal frequency. And then I'm going to use channel 1, right? Write a C program to create the PWM pulse with the frequency of 50, and exactly what I did in example 4 right in here. But now I'm gonna, instead of manual calculation, I'm gonna look into it through the programming. How do we do the exact same like performance through programming? Pay attention, this is C programming, right? So I'm gonna include my header file. Therefore, I can start writing inside my void. Inside my void, if you are looking for channel 2, therefore, just go ahead, turn on your channel 2. I have been asking here, okay? I'm just activating my channel 2. And then if I'm looking at the pre-scaling, I already calculated this one is 30. I get it from my calculation. Therefore, I'm going to say, my PWM clock is 0 times 30 because I calculated my pre-scale right in here. And then I'm going to start from 30 and I'm going to scale, like, for example, each time by 2. Then I'm going to next time have 32. Next time, I'm going to have like the clock SP. I already have the clock SP from the previous calculation. This is the clock SP. I have it from this calculation. Then I include it right in here. But in the lab, if you do not have all of this information, remember I said, I'm going to give you these registers. And I get you to look at the clock SA and look at the register information from the manual. And I'll get you to look at all of those bits. And based on what is the question asking for you, just come up with some information for either of these registers and calculate all those hex equivalent. So in case you are wondering, how do I get all of this information of 0x30, 32, 4, and so on, I use the same register information. I get them, like, for example, if I want divided clock A by 2, then simply means I have to put 1 in here and the rest are going to be 0. Then I have to convert it to hex equivalent and then I have to include it in the code. If I'm asking for by 4, then I have to leave this as 0, turn this 1, 1, and so on. So all of those hex equivalents that you are going to see right in here inside the code, I'm getting them from that register file information. Each time I toggle one of those bits to 0 and 1 based on what I have been asked, I calculate the hex equivalent and I command it. For example, to clock a scale, for clock a scaling based on the register information, I have to just put 0 and 1 and then calculate 32 as a hex equivalent. For high, to turn it high then low, I call it PWM, POL standing for polarity, means I'm going to just turn it 1 and 0. Therefore, I have to just, for example, again, I have another register for PWM, POL. I have to go ahead and look at PWM, POL. And then from the POL, which is this one, this is my PWM polarity register. And then from the polarity register, I have to see which one. If I want the output channel to start low, then I have to put 0 in the output channel. If I want to start from high, I have to put 1 and then accordingly calculate the hex equivalent. Did you get the point? So every single line in that piece of code is just putting 1 and 0 in this bits of the register based on the requirement, right? For example, if you want to look at the control register, for control register, you have again an 8-bit register in here, but look at here. This bit 1 and 0 and 1, and of course this 7. These are by default 0. These are by default deactivated. I have nothing to do with those 2 bits. And all I have is from bit 2 to 6. Therefore, if I want to keep PWM channels separate, means if I wanted 8-bit, I have to put 0 in here. If I want to just keep it the PWM X and Y together, then I have to put 1 and make it 16-bit instead of 8-bit. Therefore, do not get confused when I say, for example, for clock also. For clock, look at here, you do have the register file, you do have the table, and I'll give them to you inside the lab, and I'll get you to, for example, go look at value of clock P. When I say look at value of the clock P, first you have to have like bus clock divided by 2, then in PCKB, 0 means here, put 1 in here, 0 in here, 0 in here, and the rest are gonna be just all 0. Now, all you have to do, divide them to 4. 0, 0, 0, 1 means what? In binary. 0, 0, 1 is what? Pardon? Just convert it. Just convert it. This is for PWM CLK, right in here. PWM CLK. Select clock SPB. If you want to select clock SPB, it has to be 0x04, right? And so on. So all of this hex equivalent you see right in here, I've mentioned right in here, all of them are coming from toggling those 0s and 1 inside the register. So now for duty cycle, all you have to do for different duty cycle, all you have to do, you have to command PWM DTY. Like, for example, for if you want it for 30, in this example, I was asking for 30. That's why in here I mentioned 30. If you want it, one more time, somebody just tell us, what is duty cycle? When I say like 60% duty cycle or 30% duty cycle, what does that mean? Pardon? The time the signal is on. When I say keep it for 60% duty cycle, suppose this is your signal. If this whole thing is going to be 1 period or 100%, when I say 60% means 60% of the, like the whole period, the signal is on, and then only probably 40% in here. This is not really accurate, but just for your information. So when I say 50%, then 50% is on. This is the on or 1. This is the off or 0, right? But the time that we say for duty cycle is always mentioning the on time, not the off time. Make sense? So now, let's look at just a quick review to initialize the PWM module. What I'm gonna have right in here, and this is exactly what we need also tomorrow. So in order to choose the resolution, remember, even in the previous labs, I said we can choose the resolution. We can just select 8-bit or 10-bit. What's the difference? If I'm having a higher resolution as 10-bit, I will be able to turn on that RGB on the corner of the setup. Remember, if I'm having less resolution like 8-bit, definitely I won't be able to turn that one on. Still, I'm having an 8-bit. That's a different thing. Do not confuse resolution with the register bits. Register bit is always 8, but resolution, I'm gonna just increase. If I'm having 255, means this is an 8-bit. Now, if I'm gonna find out the period, C and T stand for counter, kids. C and T stand for the counter. If I'm gonna look at the counter or the period of the counter for PWM, all I have to do is I have to consider the period time. Period time means exactly like this. This is my T period or period time. And then for an 8-bit resolution, we always have 8-bit means what? 2 to the power of? Yeah. Then it becomes 255. Makes sense? Right? So then if I'm going to find out the divisor, the total divisor, we have only one equation in here. And I'm going to practice this one inside one example for you instead of just looking at this slide. Therefore, we are planning to look at the period of counter. T stands for the time, which is the period of the counter. And then the total divisor means the period by the bus clock. And then we are going to have like the PWM ER, which is going to be again the clock period, And finally, we can calculate the number of counts. Now let's do this using an example. Example 6. How do we do all of those stuff? I'm going to choose all registers. So this question is asking me choose all of your registers for PWM to generate a PWM waveform. What does that mean? PWM waveform means just 1 and 0, right? I'm going to generate some square wave. Any square wave could be considered as a PWM waveform, right? Therefore, I'm going to look at the channel 1 with frequency of 20 kilohertz and a high duty cycle of 10 microseconds. Assume the bus clock is 8 megahertz. Using those information, let's look at example 6. So how do we do that? I have to consider that I'm going to go back to slide 17 quickly review. I showed you this one before, but one more time. Look at what I've got right in this example. This is the basic register functionality for the PWM programming from the data sheet. Look at this. This one in here, my bus is going to be, look at here, this is the bus clock. For us is 8, right? And then I'm asking for the duty cycle. PWM register for the duty cycle. Remember the question was 10 milliseconds. And then I'm supposed to look at the divisor. This is what I'm going to calculate. So I'm going to send the 8 to the divisor, to the divider. The total divisor in here should just send some information to my CNT. Remember I said this is going to stand for the counter. And then what I'm going to have from the PWM, PER register, I'm going to have 20 kilohertz right in here. This is the plan, right? So let's do it now. And remember, the output is always just a PWM waveform. Based on this, let's go do it step by step with some mathematical calculation. So what I'm going to have, I'm going to consider the frequency, the PWM frequency, which I'm going to call it PWM. It's going to be like 20 from the question. This is 20 kilohertz. 20 kilohertz, if I have only this one, I do have enough information to go ahead and calculate T period. What was T period? I just had it in here. T period. This one. Right? I can just calculate this one or this one. So now, remember it was 1 over the frequency of PWM. What was the frequency of PWM? Therefore, you can simply say this is 50. Makes sense so far? So Right after that, now I can just calculate the duty cycle. PWM, duty cycle. If it is like 10, it was given 10, right? 10 microsecond. If it is 10 microsecond, then I'm going to say D, or the duty cycle, is 10 microsecond over, I already calculated T period. T period is 50. Kids, one more time, duty cycle is given in the previous slide. Duty cycle is 10 microsecond T period. This is the T period, and this is the 10 microsecond, and this is the, no, this is the T period. And then your 10 microsecond is going to be your duty cycle time of 10 microsecond. Duty cycle, this is the time, and then this is the T period. Then you can calculate the duty cycle. So if you do so, then this is going to be 20%. Now I'm going to look at my main bus. Main bus, or let's say the frequency of bus. We already know if we have crystal frequency divided by 2, crystal frequency divided by 2 is going to give me like the bus frequency. Therefore, I'm going to have the, in this example, I'm going to have it to be the bus frequency to be 8. It's given to be 8, right? From the problem, look at here. Therefore, I'm going to consider it 8. And then from there, I could say now T bus is going to be 1 divided by 8, which is going to be 0.125 microsecond. So far, so good? Yes or not? Let me just draw this one. Yes. Which one? Give me 1 second. Okay. Here you've got this one.
Yes, like,
this one, this line. Top line, 20 kilohertz was given, right? This one. And then I have T period, which is going to be 1 over, this is kilohertz. Remember? So then it becomes 50. One divided by 20 kilohertz becomes 50. Isn't that? Yeah, it's second. This is time. It's second. No, it's second. It's second. This is second. One more time. This is second. As it is mentioned right in here. Microsecond. I keep the same unit. Now make sense? Okay. So we can move on now. Now, let me derive first. If I have time to be here, and then if I'm going to derive exactly what I wrote in there. So if it's supposed to be 10, suppose this is going to be my 10 microsecond. Kids, this is microsecond. Do not confuse the units. And then I supposed to look at here, I had it 50. And then if I'm going to go to 50, and then I'm going to have to 10 supposed to be the on time, right? The high time. The high time from the problem, I'm going to highlight it. 10 supposed to be high time. If 10 supposed to be high, means I'm going to have it like this. This is 1 means high or means on. And then I'm going to have this one to be on for 10 microsecond. I already have this part of it. Makes sense so far? Then the remaining is going to be off time. Means right in here. This is my on or 1. And then this is my off or 0. Now makes sense? Now, next, what I'm looking for. Now I'm supposed to just, in a step 1, select the largest PWM. I'm supposed to select the largest PWM. Therefore, I'm going to calculate it. And then I'll draw the difference between them. So I leave a little bit of room right in here. I'm going to continue after I have the count. This is going to be my count or CNT for the PWM. Count or PWM CNT. And then, which is going to be still time, okay? Count is always based on time. And then I'm going to calculate first, select the largest. Step 1, this is important. Try to learn this part. You have to first select the largest one. Select the largest one first. The largest what? The largest PWMER. Remember, I had scalar and pre-scalar starting from a minimum and then stopping at the maximum. That's exactly what we are going to do. And this is included in your in-class assignment on Thursday. Therefore, pay attention to learn it. So then I'm going to have 8 bits from the question. I'm going to have 8 bits PWMER. Therefore, I could say my PWMER is equal to, since this is 8-bit, 2 to the power of 8 minus 1. And that's why we have it 255, right? And then in a step 2, what do I do? In a step 2, I'm going to find the PWM counter period. So this few steps that I'm just going through, it is going to be exactly the same for every problem. So you have to go through all these steps. At step 2, that's why I leave you some notes in here. Find the PWM counter, right? Counter for what? Counter period. Find your period. What does that mean? Means T. I already had it in here. T PWM CNT. Counter period means T for PWM CNT. And this is in here. T PWM CNT. Remember this one? This equation is given in the lecture slide. Now let's do that. For PWM CNT, then you have to say T PWM CNT. Remember, we had it 50 microsecond. And then divided, we already calculated the ER right in here, 255. I use the exact same number. And then it becomes 0.196 microsecond. So far, so good. You get it? Now, how about the step 3? Now it's time. Let me highlight them. This is a step 1. This is a step 2. Now I'm going to, in a step 3, what I'm going to do, I'm going to calculate the total divisor. So calculate total divisor. I already have the equation from the slide. I use this one. Total divisor is like the T counter divided by T boss. I use the same equation. So I'm going to highlight, this is your step 3. And then in a step 3, I say total divisor is equal to T PWM CNT divided by T boss. And right now I have both of them. So I'm going to have easy experience. I already calculated 196. So I use the same number. And I've already calculated T boss, which is 125. Remember, I calculated that one right in here, 125 in here. I take it from this calculation. Okay? You follow? Everyone follow? So then right in here, I'm going to say now what's the answer. Then this is going to be No, actually it's 1.57. Now, I can calculate or I can select the higher possible integer for total divisor. Do I have 1.57?
Yeah.
No. We have to round it. So in order to select, I have to say select the higher. We have to choose the very close divisor, the higher or the highest possible, that's why I say possible, integer for total divisor. Since we do not have one with decimal point, I have to round it up, and then I'm gonna say, I'm gonna consider 2. Makes sense so far? Now step 4. I'm gonna highlight this one. In a step 4, I'm gonna recalculate the PWM counter period. PWM, C, and T. I have to recalculate because now I have the divisor. If so, then I'm gonna say the total divisor. Now I have the total divisor, so I'm gonna recalculate. It's gonna be T, PWM, C, and T over T bus. We already did it one time, and in a step 4, we can recalculate. Now I'm gonna say, I'm gonna rearrange because I'm looking for this one. And I do have the total bus. I do have it. Total divisor, I calculated, it's gonna be 2. So now I can say my T, PWM, C, and T. If I rearrange, it's gonna be 2 from this calculation. And then it's gonna be 0.125 from my previous calculation. It's giving me 25 millisecond. Make sense? Yes or no? Now, I'm gonna go back. So far, I have some of the information to come back here and a little bit more information I can add. So I'm gonna continue with this one to be the same. Suppose this is my 10 millisecond still. This is my on time still to be 1. I keep it as it is. Now I have that 196. Remember, I calculated in here. My TPWM is 196.196. Now I'm going to use that information, and I'm going to say, in here I'm having, suppose, 100.196 millisecond. Therefore, I'm going to continue this line. Right in here, it's going to be the same. And I'm supposed to stop at 255, which is going to be 8-bit PWM-ER. 8-bit PWM-ER is right in here, I calculated. 255. So all of these numbers, which I'm adding to this graph, I get them from my calculation, okay? So this one I set from where the 255, I get it from my step 1. This is my step 1. And then right after that, now I'm gonna look for the time in here and the time in here. These are the next step that I have to calculate. How long it take, right? Or how long is 0.190 second, but from what point to what point I'm gonna calculate. Let's go do that calculation as a step 5. A step 5, I'm gonna recalculate. I need to recalculate again to find that. Step 5 is going to be recalculate the PWM ER. In order to find from what point I'm going to have that 0.196, right? So I have to recalculate right in here. Therefore, I'm going to say the same equation, PWM ER equal to, remember it was T period, same thing, right in here. I get it from this equation, right in the lecture slide. So I have to say T period divided by T, PWM, C, and T, the exact same one. So T period was 50 milliseconds, I just show you. We calculated this together before. And then the 25 milliseconds, I just calculated in here. I use it, so I put it down like in here. So I get it from the previous step, step 4. And then this becomes the 200 counts. Therefore, I can now go ahead and say it takes like 200 counts. For example, if I draw it right in here to not to go back, if this is my PWMC and T, then if this is the duty cycle, means if I have 20% on, and then if I'm right in here, then I'm gonna have 20 counts from here to here. I have PWMER to be 200 counts now. If you want this one in the previous, right in here, it becomes this point. This is 200 now. Now I need to continue and calculate the duty cycle, right? Let's just go. This is my step 5. Let's just add one more step. Step 6. In a step 6, I'm going to calculate duty cycle. Let's do this together. So how do I do that? We already know, I just show you duty cycle, even from the question, it was given, right? Duty cycle is 20%. If the duty cycle is, we calculated, is 20% from the question and calculation, then I'm going to have the PWM DTY standing for duty cycle, 20% times my ER. I just calculated ER in here. Remember the 200. I take this one, put it down. 200. PWM ER. I mentioned in here, this is my PWM ER to make sure no one is confused where I'm getting that. And then if so, then I'm going to have my new duty cycle to be 40%, right? Make sense? Yes or no? So this is going to be my new count. So if that's the case, I believe at this point, anyone who has a question, let me know. Did you get it? Yes or no? Nicholas, question? You look like you have a huge question in mind. If so, ask it. So I have to go always through this 6 step one more time. I'm gonna just minimize in case, I'm not pretty sure if I can show all of them at once, but at least just have, yeah, I can. So look at here, I went through 6 step I highlighted in order to calculate my largest one, my largest PWM-ER, and then I calculated the period, the PWM counter period. This is my counter period. And then I calculated my total divisor. And after I have the period and total divisor, I have to recalculate my counter. Then I recalculated the new counter. And then right after that, I have to again recalculate my new period, right? My new period. Using that one, I calculate, then I have 200 counts from the beginning of on time to the end of off time. And right after that means anything after right in here is going to be like, for example, this one is going to be 201. That's going to be my count, 201. Each count takes this much. This is the time that it takes for each of my counts. Make sense? If I have the time for each of those counts to be 0.196 microsecond, then my next count right in here is 201, and so on. So now let's look at another example. Another example is asking if the generated PWM signal in example 6, you have to understand the one I did in order to connect the dots for the next one. If the generated PWM signal in example 6 is used to control a 12-volt DC motor, like the one that you have in the lab, with kV, this is a constant, this is a standard constant, which is equal to 440 RPM, right? Then find out the precision of the speed control for the DC motor. So let's do that then. This is going to be example 7. I'm having only this example for today. Then the next one, I leave it for you in case you are interested. You can do the calculation for next one, example 8 yourself. That's extra. But I'm going to do this example for you. So I'm going to look at example 7. So in this example, again, I need to go back to the microcontroller structure. So let me quickly draw that one. The microcontroller, suppose this is your microcontroller. If you have this understanding, things become a bit easier to understand. Then I'm having a PWM. And of course, that one, it was 20 kilohertz from the previous. It is asked to look at the previous example. So then from there, it is 20 kilohertz. And then I'm going to look at, remember the optocoupler I show you in the lab and I introduced even last week. Then this one's supposed to be connected to my kids. What else I can call instead of optocoupler? Remember I said optocoupler could be just even MOSFET. Yeah? Okay, that's just a reminder. So I can even use a MOSFET. But we have an optocoupler, so then I use optocoupler. But it could be MOSFET as well. Then what else do I have? Then from here, but this one has like, I'm having some resistance in here, remember? This is my resistor. So this signal is going to my optocoupler. And then in here, I'm having some sensor to detect it. I show you in the other lecture, the structure. I'm just trying to review to make sure you know what I'm doing right in here. And then this one's supposed to be connected to my DC motor. Symbol for DC motor usually is like that. Not exactly like this, but very similar. Forgive my drawing. And this is going to be 12 volts. So this is what we are going to do. So this is my DC motor. Right? And the information in here is 0 to 12 volts. Always information is given, minimum and maximum for any devices, supposed to be provided by the manufacturer. And from the question, I have kV to be 440 RPM. Right? So now, what I'm going to do right now, and remember, microcontroller, I said it before, I repeat, microcontroller is minimum, maximum also given. 0 to 5, right? This is the max, or in some microcontroller is 3.5, but the one that we have in the lab is 5. So now let's look at what is this one? This is the sensor, remember? This is a sensor to receive light. This is inside the, go back to the previous lecture, I show you that we do have like one sensor to receive the light, and we do have IR sensor to send, IR sensor or IR LED to send the light, to emit some light, and the sensor is receiving it, and that's how optocopper can optimize the voltage. I explained it in previous lecture. I just remind you one more time. Now, let's just go ahead, look at the PWM. So first, maybe I'm going to look at, these equations are important. Let's draw one equation. For RPM, what do I have? KV, KV is like in here, not the times V average. And this is going to be my first equation. I'm going to say this is my equation 1. Keep it in mind. Then I'm going to calculate this V average. I don't have it. So from the equation that I show you in the previous slide, in this lecture, I remind you, I have dVH plus 1 minus d. This is included in the previous slide. If you go back, I taught it last week, VL. And then this is supposed to be 12d. Why is that? VH is 12. I get it from here. This is my VH. This is my V high. This is my V low. Then I get it from there. Do not go confused or think where I'm getting this one. This one is 12. That's coming from the DC motor information. So I put down 12 in there. If I put down 12 in VH, and then, as I said, VL is like 0, then I'm going to have 12D. Make sense so far? If I have 12D, just from there, I can say V average is going to be 12 delta D. Delta D means the smallest increment of duty cycle. This one is my smallest increment of duty cycle, right? Now, I can say what is my RPM now because I have that one. RPM, remember this is my equation 1 from the E1. I can now calculate RPM is going to be KV, and KV was given V average 12D, and then I can say delta RPM is 12 kV, and what is my average right now? Delta D, right? And kV, remember it was given, kV was 440. Look at here from here. kV is given. Therefore, I can just say, what is this? This is 440 from the example. And then I can now calculate. This is going to be 5,280 delta D. Now from the PWM. What do I have? I have duty cycle. Duty cycle resolution. Remember, I calculated and I said it takes like 200 counts. Therefore, I can say now 1 over 200. This is coming from example 6. I calculated that is equal to delta D. Now I can go ahead and say delta RPM. I can rearrange RPM is equal to that number I calculated, which was 5,280 times 1 over 200. This is going to be 26.4 RPM. Make sense? Now let me draw it for you. What I said means this one. Remember maximum or V high. This is going to be my V high. It was 12 volt. This is my voltage. If maximum is 12 volts, and in here VL is 0, What does it mean? All of these calculations means what? And then right in here, I have delta V average. I'm going to calculate this one, which is why I did it. Delta V average is this one, delta V average. And then I calculated delta RPM. Delta RPM is this one. Delta, this is my RPM. And this is my delta RPM. Now you just connect them for the minimum and maximum, right? And then the KV. KV, remember, it was a constant. If it was a constant, I should write like this. Means this one is KV, which is 440 RPM per volt, right? I calculated this one to be the maximum. This one is the maximum for it to be 5,280. This is this calculation, maximum RPM, right? And then in here, the maximum was, I'm going to move this one, V high. This is the maximum in here. This is V high, which is 12 volts. For the maximum 12 volts, I'm having the RPM to be 5,280. Now makes sense what I did? So now, this one is going to be the like equation 1. And then if you just use the equation 1 and then you 12, I have this 12 D. This is going to be, for example, another equation. And then these two equal together, it can give you this maximum, and it can give you your delta RPM. Delta RPM means this one. This one I calculated, and this is 26.4 RPM for each of those minimum, maximum. Make sense? So I'm done with all of this information in here. I'm going to close this first half of the class right in here. I'm going to pause, and then I'll come back in the second half with a little bit more information about the stepper motor. Therefore, while I'm going to give you some break right now, still I'm available to answer any of your questions. You may want to go for a few minutes of break, and then we'll resume with stepper motor. So let's continue with the stepper motor. First, I'm going to explain what's the difference between stepper motor and DC motor. Any idea, kids? May I have your attention? What's the difference between a stepper motor and DC motor? In fact, I would say a stepper motor is a type of brushless DC motor. Therefore, the only difference in here is going to be when we are planning to create incremental motion, we have to just use a stepper motor. Again, stepper motor is a brushless DC motor. That's the only difference in here. And then we are going to look at the rotation and divide the rotation to multiple equal steps. That's the only difference between a stepper motor and DC motor. So a stepper motor provides, as I said, incremental. I'm going to write it. If you want incremental motion, we have to use stepper motor. Because except stepper motor, sometimes they call it step-in motor. Either will be okay. And then a stepper motor is just a brushless DC motor. Both stepper motor and DC motor, in fact, they are some cheap, or I would say low-cost motor, but they do have different application, more specifically in automotive design, or I would say automotive engineering. For example, what? Who can just maybe just use some of the example on In which part of automotive we use, for example, a stepper motor? Some example, like for example, for your side mirror positioning. Side mirror positioning, we use a stepper motor. We do it incrementally. We don't do it directly. Another example, who can tell? For windshield, like washer fluid, for that one also we use, yeah. Yep. And then that's why the other day I said, when you are defining your final project, especially since we are practicing both DC motor and stepper motor, you can look at the actual real functionality of all those components in the automotive. And then you can come up using those devices inside the lab to demo different parts. For example, as I said, for side mirror, you can definitely use your stepper motor and then come up with some story behind it and show like the side mirror repositioning, or your windshield, like I would say fluid flow. All of those, or even in the actually for regulating your intake, that one also stepper motor, many more. These are just a few of them on top of my mind, but many more applications. In here you can see that for the valve positioning, I have one example in the lecture slide for you. This is for the valve positioning. We use a stepper motor. For the engine control, for the feedback of the engine control, we use a stepper motor and many more. And again, since we are going to look at incremental motion, we do need to convert it to to use brushless DC motor in order to do so. So now let's just look at, and what does that mean when I say we need it to happen incrementally? It means we need to just divide it to equal position, each of them a certain angle based on that certain stepper motor. Let's look at the construction of a stepper motor in case you haven't just discovered that before. A stepper motor is a digital input. Digital input, output. Even the output, why is both of them? Because as I said, it's going to be a step. It's definitely by default 0 and 1. Therefore, it's a digital input output. So we can simply use it for any application that controls signals as a digital pulse. But remember, for the DC motor, last week I said, DC motor by default is not digital, it's analog. But here by default is just digital. So one digital pulse to a stepper motor divide, or let's say if you have it like two-phase, two-pole, sometimes you do have it like largest size, simply means you can see the operation principle of two-phase. We have two types of permanent magnet, bipolar or unipolar. When I say PM means permanent magnet. When I say, for example, two-polar stepper motor, simply means I'm having two-phase and two-pole. There are situations I'm having like 4 of them like this. Then I have, let's say this is south, north, and then this is south, north. In that case, I'm having 4-pole. Or I can have 6-pole, or I can have 8-pole. Like out there in the market, you can find different size of it. So here, the one that you can see, this one is a two-phase unipolar permanent magnet type stepper motor, which I am using it for rotor and coil. Therefore, you see that this stepper motor has like in total 4 positions to go around. I'm moving from B1. Suppose this one is like A2, this one is B2, this one is A1. I'm moving from B1 to B2 through these steps. If this one is north, next time in here, north will be in this direction, south in this direction. Next time, if it is moving this way, clockwise, north and south, from here to here, they change their position. And the same for A2. So this is going to energize in the first step. If I energize B1, what do I mean with energizing? It's a motor. Energizing means VCC, or the power source, is connected to one of those magnets. This is permanent magnet. So for example, if I connect the power source to B1, means initially B1 is energized. If this one rotates, by default, you do not disconnect it manually and connect it to another one. You never do it manually. When it is rotating, next time A2 is connected to power source. And that's how we say this is increment, or this is pulse. It is moving, and each time one of those poles is gonna rotate the direction of south and north, and of course it will be connected to the power source. So a step one, phase B in here, if this is a step one, phase B of a two-phase stator energized simply means this locks the rotor in the position shown right in here. It will lock in this position, and B1 is energized. In a step two, it's going to be otherwise. This one will be locked. A2 will be locked right in this position. And then in a step three, phase A is turned off. This is my step three. This is my phase A right now. It's connected to nowhere. In here it was grounded. In here it's connected to nowhere. Now ground is moved to B1, and now the energized one is like B2. And so on. In a step 4, phase B is turned off. This is a step 4. Now phase B means this whole phase, regardless of B1 or B. This is off. And now on is A. This is phase A, which is on. Each time one of the phases go on, the other phases, and it is only two phases, and the other phase will turn on. And of course, the sequence causes the rotator or the rotor, we call it either rotator or rotate, to rotate in here. I'm having 90 degree because I have only two phase, two pole. Means this is 90, this is 90, and all of these angles are 90 degree. If I have a different size, like for example, two phase, three pole, or yeah, then all of those is going to change accordingly. Now let's look at how I calculate it. So suppose that I'm going to look at the step angle. A step angle one more time. A step angle, if this is like a two pole, two phase, means this one. This is one angle. This is one, this is one, this is one. If I'm going to calculate the step angle, each time I have to say 360 based on number of the pole times number of phase. Number of pole times number of phase. This is how I can calculate a step angle. 360 divided by number of pole times number of phase. In case I'm having, let's say, 2 by 2, like this example, let's do this one as an example. Since this is a 2 by 2, means two phase, two pole, I should say 360 divided by 2 times 2, then I'm going to have 90 degree. Now you know why I said this one is 90 degree. Makes sense? Now, if you do have a different one, if you have a still number of pole to be 2, number of phase to be 3, then you should have a different angle and so on. Make sense? Now, a step angle is 336 degree always by this one, and you can call this one also S. So number of phase, in electrical engineering, we call it S. S means number of phase times number of pole. If you see it somewhere, do not confuse. S is the same thing. Or you can say 360 divided by S. Now, that's one way to calculate. These are just extra for your review kids. Or I can say S is M N R. Then in that case, NR means number of rotor teeth. And now I'm going to introduce what is rotor teeth. This is number of rotor teeth. M is the number of phase. This is my phase. And this is rotor teeth. Now, what is that teeth? That's why I introduced this one. Teeth means this stuff. How many teeth I have? Right? In order to calculate that S, you need to just know how many teeth you have and how many phase you have. Make sense? This is a little bit, I would say, more beneficial for even your capstone project. You can simply calculate it like that. Now, look at this one. If I have, for example, a 4-phase. 4-phase means what? This is a 4-phase, means I'm having 1. This orange one is 1. This red one is 2. This blue one is 3. And then the green one is 4. That's how we can say I'm having 4-phase. If I have 3, means I have 3 pair in here. This is one of them. This is 1 phase. Red one, 2nd phase. And the green one, 3rd phase. Do not confuse the number of phase with the number of teeth. Those two are completely different. For example, in here, I have 3 phase, but I have 4 teeth, right? Do not confuse them. Now, there are few methods to increase the stepper motor precision or accuracy, which is going to be a focus for next lab, which is focused on the stepper motor. In order to increase that accuracy, we need to have, for example, using half a step derived. So the step angle for a given stepper motor geometry is cut in half. You can see it in here, like, for example, one of the method is micro stepping, or you can just divide it by half in order to just look at the angular resolution or increase the accuracy. That's one method. So the step angle for a given stepper motor geometry will be divided by half a step, and simply means half a step will create more accuracy, because in here you are gonna have, if it is half a step, in here your number is gonna increase. If the number is increasing, then you are gonna have more accuracy. Means instead of collecting information for a full step, now you have 2 information for a full step. Instead of 1 information, you have 2 information for a full step. If this is a full step from here to here, if you divide it by 2, this one is 45, this one is 45, then instead of just receiving 2 maybe results, receiving 1 result for a 90, you receive it every 45 angle. That's how you can increase the accuracy of the stepper motor. Another method in order to do such a accurate measurement or precision is going to be looking at smoother motion. Looking at the smoother motion means consider micro stepping. Means even more than half divided by more than half. That's how, for example, in here you can see this is a 2-phase 6-pole. 2-phase 6-pole means, look at here, still I have 2-phase, but 6, 1, 2, 3, right? 3 by 2 is gonna be 6-pole. So I have 2-phase. 2-phase means the magnet part. This is 1 phase, this is 1 phase. Phase is talking about the magnet part, right? And then in here, I'm having 6-pole. So 2-phase, 6-pole means it's moving like half a phase, each half a phase. And that's why I'm having 6. This is exactly what I said. A step size, or S, you can call it also S, is 360 And then number of phase, number of pole. This is how you calculate the step size. Any questions so far? Then I can just look at one quick example in here for you. Like, for example, this one. It's asking me if you have an angle of 2.5 degree, calculate the number of steps for the shaft to make 250 revolution, and calculate the shaft speed if the stepping frequency is 3,600 pulse per second. How do we do that? For part A, let's just calculate this one. For part A, asking me to have 25 revolution. So I'm going to say revolution is going to be, what was the size? It was 360 divided by 2.5. Means I'm having 144 steps per revolution, right? So resolution, revolution, do not confuse them. Resolution, revolution. And then now in step two is asking now, a step per revolution is 144. Now look at the required calculation in there. Then I'm going to say, in order to calculate the 25 revolution, for 25 revolution, what do I need? I need this 144, which is the resolution, times this 25 from the problem, which is going to be 3,600. How about next one? Next one is asking now, look at the stepping frequency of, I already calculated this one. Now, if that one is 3,600, look at the shaft speed. So in order to do next part, for shaft speed is 25 pulse frequency resolution. Now I can say M is going to be B, which is these two. I consider this one B. Then I'm going to say N. If I call this one B, that 2.5, remember, that one is the step angle. If my step angle, or call it beta, then say N is beta, which is the step angle, times the frequency, divided by this 360. Then you can say, I already have the beta, or the step angle is 2.5 times 3,600 divided by 360 degree. I can calculate the RPM now. 25 resolution per second. Make sense? RPS, resolution per second. You can write resolution. I have 25 resolution per second. Done? Next, let's look at a little bit of, I'm gonna just maximize this one. Let's look at a little bit of like the variable reluctance stepper, reluctance of any magnetic circuit, which most of the time we do have like a stepper motor. Anytime that you do have a coil is this one. Any wire which is rounded around some pieces, we call it a coil. This is our coil. Then we call it just magnetic circuit. We do have some magnetic circuit in here. And in this magnetic circuit, we have to look at the reluctance, which is happening by rotation of these coils, right? Anytime which is going to rotate, this teeth, I already said we call them teeth. These are my teeth. And the teeth could be different based on the number of teeth could be different based on that stepper motor. This reluctance will change by the number of the teeth, because it is going to move in some angular position around the rotor. This is going to be your rotor or any rotatory part of the stepper motor. We call it rotor. And these teeth are around the rotor. These are the teeth around the rotor. So now looking at that one, we can say how the reluctance is, principle of reluctance is dependent on the multiple location of the rotor device, because when it is moving in this direction, is happening in multiple location, and that's how, based on that multiple location, it is going to just generate some reluctance. Very similar to if you have any wire and there is some electrical pass through the wire, it's going to be very similar to flowing current through a wire. Therefore, this one is moving, reluctance is moving, and then each time, so if the current is flowing through a wire, it is going to be like, for example, this wire is just generated in here in a format that we have multiple rotation around this. So it's the same wire, but if we have more number of loop in here, we call it coil. If it is a single one, we call it maybe wire. So it's very similar to the electric currents. Inside this and wire has resistance. Inside this wire or inside this coil in here. So next is about simply means if we minimize the length of the reluctance, means if we minimize the length of the reluctance, we have more gap. Minimize the length means I'm going to have more gap in here, more gap in here. If I have less teeth, I have more gap. More teeth, less gap. If I have less gap, accuracy is higher. If I have more gap, accuracy is lower. Make sense? Let me just look at this one, and then we are going to finish it up. With this one, you can see even the teeth is more obvious. If we have less, we have more gap, right? If we have less teeth, we have more gap. So let's look at the sequence of pole in some variable reluctance. Variable reluctance, once again, means different position of this teeth. These are the teeth. If this is maximized, the same teeth in here, it is maximized in here. If this is the teeth, if they are in variable position, and these are the poles, through the poles, they are going to generate variable reluctance. Therefore, principle of variable reluctance, as I said, is dependent on the position of these teeth toward the pole. So, now look at this one. This is the sequence. If I start from here, this is my coil. This part is the rotor. And then suppose you start from here. And then now this one is energized. This pole is energized. Next time, when this is moving in the clockwise direction, this pole will go off. This one will energize, which is going to be here. Now this one is on. And so on. If moving to the next one, this is the direction of movement. Now this one is off. In here, this one is on. And so on. Now suppose I have more pole, therefore I have more on and off. If I have more on and off, means I'm generating more pulse. If I generate more pulse, means the accuracy of the signal is higher. Now make sense? Why or how we can increase the accuracy. So let's look at this one. This is a bipolar stepper motor. It's another type of a stepper motor, but the difference in here, I have a single winding per phase. A single winding. What do I mean when I say single winding? It means this one is going to here, and these two are connected. Means In here, one is always getting out, and these two are connected. That's why we say we have a single winding in bipolar stepper motor. So it has generally 4 wire. So unipolar has 6 wire. This is unipolar. Unipolar in here, look at here, I have 6. But if I have bipolar, I have 4. This 4 means 1 between the 1B and 1A is in common. In here, I have 1 common in here. This one is common. And then from here, I have 1 going out. And then from the other one, I have 1 going out. But in here, I had 1 common in here, another common in here. That's why I have only 2 common, 2 out. 2 common, 2 out. 1 out from here. If you trace the line, this is 1 out, and this is 1 out. The other 2 are common. In here is different. In here, I have 2 common. 2 common and 4 out. Make sense? That's the difference between bipolar and unipolar. Unipolar, pay attention. There are situations unipolar can have even 8 wire. Unipolar, sometimes it has even 8 wire in some settings, but bipolar is always 4. That's the difference between these two. And the one that are coming out is always ground. Look at here. This one is the ground, which is coming out. This one also is ground, which is coming out. Not the common ground. Each of them supposed to have their own ground and their own positive. Their positive could be common, connected, but still they must have their own ground. This one is also ground, and then this one in common. This one has its own ground, and this one in common. Right? Their ground supposed to get out individually. So next, this one is helping you really. This slide is really helping you to just understand the full step from for microcontroller. This is easy to understand. So if you have like A, B, C, and D, simply means in here you do have 2 pole, 2 phase. 2 pole means north and south, and then you have 4 phase. 2 phase means this is 1 phase and this is 1 phase. So you have 2 pole and 2 phase. Now, a step 1 is winding A is energized, means VCC is here. In a step 2, VCC is like in here. In a step 3, VCC is here. And a step 4, VCC is here. Therefore, means each time one of them is on, the other 2 on the opposite phase. If it is a step 1, if this is A and this is B, A is 1, B is 0. If this is C, suppose this is 0, so this is 1, 0, and 0, 1. In each phase, one of them should be 0, the other one should be 1. And the 1 is always the one that it is connected to VCC. And the 0 is the one which is grounded. Same for a half a step. Half a step, you do have more. Remember, if in there you have 4, half a step means you are going to increase the precision, therefore, or the accuracy, therefore you have to double it. You have to continue from here to 8. Then simply means this time, each of them may go on 2 times and may turn to ground 2 times based on just a movement, like clockwise movement. I'm going to summarize this like in this example, and then I'll close it. So this is exactly what we are going to practice inside the lab. If you have your switch to be turned on, right? Then your stepper motor is supposed to, switch is connected to where? Suppose this is your microcontroller. And then you do have like your other devices. For example, this is your stepper motor. This is your motor. And then in here you have motor driver, right? And then of course this has to be connected to some source, the power supply that you do have. And then it's going to do some step. So you have to connect, like, for example, everything. If you have a switch, your switch will become your input, and then your motor becomes your output. Now you have to program it in order to monitor the status of the switch. You have to program it through the steps. If the stepper motor is clockwise, that would be everything based on in here. Clockwise means in here. Therefore, you have to start from port B, give it delay, and then in port B next time, each time based on this table. Either of them 1 and 0, 1 and 0, and convert it to hex. And then command it accordingly for port B. The only thing that is changing is port B. If you do have a two-pole, two-phase, you need to just change the port B 4 times. 4 times means this one. Either of them supposed to go 1 and 0 1 time at least. Next, if you want it counterclockwise, again, still you have to look at port B, but backward from here to here. Means this one now becomes your 1, this one becomes your 4. Everything is the same, delay is the same, but just the port is commanded backward. In here, first it is 66, right? And then you stop at 33. But now you say 66, 33, 99, and then CC. You just command it backward. And that's how you can have just clockwise and counterclockwise in your stepper motor. This is exactly what we are going to practice inside the lab. And this one is the holding torque. Holding torque means you are going to speed up to a certain point, and then you are going to hold it for a certain period of time, right? And that's what we call it holding torque. That's the maximum torque that any stepper motor can give. The maximum stepper motor torque is the holding torque. Means for how long that a stepper motor can perform or can hold that speed without being damaged. So therefore, the quality of a stepper motor is a function of for how long it can maintain the maximum speed. If that maximum is, for example, 100 or 200, for how long it can hold it. And that's what we say, that's going to give me the quality of that stepper motor. Pulling curve is just this region. For example, inside the exam, I may ask you, what is the pulling curve? You can simply say, if I'm having a maximum frequency that the motor can start from here and stop from here, like the region that this can happen is going to be my pulling torque curve or just pulling curve. Pulling means the maximum from the maximum time from the start time. How long it will take? How long it will take to get to the holding torque, and that's how long means here. This is going to be my pulling. That whole time, suppose this is going to be your gas pedal, and then you aim to reach to 100 as on a speed. How long it will take for you as from the time that you press from 0, how long it will take to reach to 100, that will be your pulling. Make sense? For automotive application. And then you have pull out. Pull out is just for how long you are going to have the, it's like the maximum frequency. And this, all of these are about the frequency. Pull in, pull out, these are all the frequency. For the pull out is the maximum frequency that you are going to stay in that frequency without having a synchronization between the start and stop. Means you're out of like synchronized speed. Your speed is not synchronized. That's what we call it pull out torque. And then what else in here? A start-stop mode means how long it will take for you to start from speed 0. And suppose, for example, you are aiming to maybe 100, to reach 200. That will be a start-stop mode. And this is not going to happen smooth. This is going to happen through some ripple. And then if you are going to just clean it off, or you are going to use some filter to uniform the speed without stopping at the end of each step, because if you stop at the end of each step, simply means you are pushing the pedal and you're trying to reach 200, and then anytime you are gonna increment to the higher speed, your vehicle is stopping. If the vehicle is stopping again, it's going to give you dangerous situation. That's why we use PWM. That's why we call it a slow like motion. Means the motor is going to rotate, but without stopping fully. It won't stop fully. It can increment. It won't. That's why we convert the start-stop mode to slow mode, to not to create dangerous situation. And in here, you can see that in order to find out the right stepper motor for any application, you need to consider the resonance area. And then it's better to have it between 100 to 200 pulse per second. Simply means the accuracy, 100 to 200 pulse per second. And of course, it is better to have like the maximum frequency, or as I said right in here, the holding torque of the motor from the data sheet before you choose it, based on for how long you want the motor to run on highest speed and how long it can just hold that speed without being damaged. And this information, most of the time, they are coming from the data sheet, and you do not need to calculate them. At this point, I'm going to close like the lecture. I'm going to activate your quiz. Simply just go back to Avenue, start the quiz,